a lot in this industry. That's basically you design customized gate for like the hash function. And just what occurred to us is that like we find that like this can actually be so you can actually get a very significant like performance over that. That is actually almost 10 times better than like all the method that we know before. So so I think to get started, I will need to firstly talk a little bit about Plonk, so that like we know why, because the optimization is for TurboPlonk, and it actually have a lot to do specifically with Plonk. So if we look at Plonk, we know that Plonk, the most basic version, or like the testable Plonk, is basically checking an equation that looks like this. We have like the selected polynomials, we have the left, we have the right, we have the output, we have like the multiplying like factor, and also the constants. That is actually also like public input, but not being shown here. But like we know one limitation. We actually always know a limitation of Plonk when we are actually only using very simple equation to define that, is that if we want to do 1000 addition, then and if you only have two whiles, two input while, one output while, as here ABC, then you actually need a lot of the gate to do that. A lot of the gate will actually translate into the actual cost when you are doing like Plonk. Like for example, usually when you have like, for example, here 999 gates, you will be paying a cost. Now we focus on the MSM because that's usually the dominating cost. You will be actually spending like 999 times like the number of witness polynomial. This will be the part of the work that you do in MSM for the witness. You also will do that for the permutation, and you will also do that for the like quotient polynomial. And by the way, usually you are not going to be doing more than 999. Why? Because when we are doing Plonk, we actually need to work with the FFT space. But here I am kind of like assuming that FFT space is not an issue. This is just part of a much larger circuit. But you can see that like 999 addition gate will actually give you basically that require a total amount of the work on the MSM that's roughly almost like 7,000. When you have a little bit like more customization, actually like the entire thing become better. So now I present a much powerful version. This one have more selected polynomial. And by the way, if you have any question, feel free to type just running, because I will probably go through Plonk, TurboPlonk, and then we will go to the hash function. So if you have any question, you can raise anytime. But if we are looking at TurboPlonk here, you can see that like one type, there are so many different types of the TurboPlonk. So here I am just using a version that like we have been using in our companies, that like we basically have 4 selected polynomial, and Q1, Q2, Q3, Q4, that is actually kind of like the original left and right like polynomial. Now we have 4 input whiles. We also have 2 multiplying like selector there, so that you can actually either multiply the first and the second, or multiply the third and the fourth. You still have the constant, you have public input, and we added a customized gate for like elliptic curve, and that's an output. So I would say that if we are still going to do addition, then actually the situation is still similar. But like one thing that is different now is that like you could actually have been doing that with much fewer gates. Actually, the number here can be even lower, because I think when I was calculating that, I was assuming that he had 3 input while and 1 output while. But you can see here that actually I have 4 input whiles and 1 output whiles. And well, but like, yes, I actually need to use one for the, okay, actually 300 is probably the right number. Basically that I always need to use 1 like wire as the accumulator. But like for the rest of the while, you will be actually passing the data that I'm adding. This will already give you, so basically we increase the number of whiles. We have like more complicated like equation. This can give you already some benefit. When you are doing this addition, you commit, actually the amount of the work that you do witness might go up a little bit because you have more witness polynomial. But you do fewer permutation. And your quotient polynomial actually is also smaller than what you are doing before. And compared with the previous one, actually this is a little bit like, so the relationship here is actually complicated, because you can see that like when you increase the number of while, some of these actually go up, some of those actually go down. But eventually we can see that like with a little bit more customization, with like more whiles, you are actually able to bring the total MSM cost here down.
Hey,
And
Weikeng, just a quick question. Are you sharing your screen right now?
Wait, can you see the slides? Can anyone see the slides?
I can see them.
Yeah.
I can see them.
Okay, so it's on my end. I'll look into it. Thanks, guys.
If you are looking at my face, then probably I think that might be a feature to switch to the presentation. Yeah. Okay, so let me continue. So now let me come to a little bit small conclusion here. Actually, so how to say that this is already an example, and that let me here share a little bit about remarks. So basically, we already looked at the example of Plonk and TurboPlonk, how you actually get everything faster. Now I want to talk about what are the conclusions that we can draw here, and also some additional remarks that we want to make. So remember that when we are talking about the MSM cost here, I actually never consider about things like sparsity, but actually in real world, some of the MSM will be cheaper than others because for example, if we look at this polynomial, QL, QR, and also this widthness, what happens in real world is that usually your selected polynomial might be actually highly sparse, so that you commit the selected polynomial if you are using Lagrange basis, actually the cost might be significantly lower than committing the entire one. So indexing can be efficient. If you are also doing widthness, sometime in the circuit that you are using, you probably have a lot of the widthness whiles, but many of them might actually be empty for a lot of the gates. You are actually not paying the cost for that in terms of MSM when you are using Lagrange basis. So basically that when we are counting the MSM cost, we also need to know that usually for widthness polynomial, that equation is probably not more complicated and will be data dependent. And the size of the quotient polynomial that we see here, for example, here in this example is 5, and in the previous example is 3. This number actually will be depending by a few factors, like how many whiles that you are doing, because that will affect the permutation polynomial, the degree of the permutation polynomial. It also also is related to the equation that you are checking. That is, what is the degree of the left side or the right hand side of the equation that you are checking when you are computing the quotient polynomial. So now we have
a question to this.
Yeah.
Just with the permutation check, how do you have any concrete numbers as to how that dependence is?
So let me see whether I have so let me actually stop sharing here and open the original Plonk paper so that we can discuss that why there is a case here. So give me 1 second. Let me quickly open that. Okay, and let me share the screen to that. So this is a good question. Basically, is that how does the permutation check actually cause the quotient polynomial to be more complicated? And I think we should be finding that right. Okay. Okay, right here. So basically, it's because of this part. When we are verifying the quotient polynomial, you are actually doing something like this. And this polynomial have several things. First of all, you do need to multiply this, so that's 1. And the number of the basically the degree here have a lot to do with the number of whiles that you are going to do. So basically, this is why the number of while actually affect the permutation check. Basically, the quotient, how the permutation check affect the quotient polynomial have a lot to do with how many variables that you are actually checking in. And that's why basically the quotient polynomial usually are decided by 2 parts. First of all, how complicated your equation is, and second, the degree that are caused by the permutation check. Okay, let me switch back to the slides. And actually here. So basically that's why the permutation check actually is also a factor, which means that if you use a lot of the whiles, and if you are using a lot of the whiles, but you are not using any of the high degree gain, then you might be actually losing some optimization opportunity. Okay, so now I will go to the next slide. So I want to point out one thing that is not often discussed is that actually you can also enforce multiple equations when you are actually doing like Plonk. And like one example is here. So so what I added now is actually adding something like range check. Basically that if like the QB selector is not 0, then that gate will actually also enforce the second, the third, and the fourth while to be either 0 or 1. And this is usually being used in range checking, because in range checking, we do two things. First of all, we check that like the bit decomposition actually match the value that you are trying to do range checking over. And the second, you prove that like these bits are actually bits. And this actually, by basically that like by just adding 3 like this like equation into the like proof system, you actually are able to already bring down the cost of range checking directly. So basically now I'm showing a more special example, range checking. If you do range checking also into this equation that later you will be using inside the Plonk to do like the quotient polynomial, you can already cut down the cost of range checking by actually about 3 times. And this is almost for free as well, because also these several like Boolean testing range checking polynomial, the degree is not that high. And when you are actually combining them in the quotient polynomial, they will only increase the cost of FFT, but it is not going to increase the cost of like MSM at all. So this is basically the idea here. Basically that like in like Plonk, you can actually add in some more equation. You can also basically use the whiles more like cleverly. And this also shows that maybe you can also just see about a hash function and think about how do you design a customized gate that actually verify that. So now I will go to this hash function. This hash function is basically based on a design like principle that like I can find a polynomial that is probably difficult to compute, but it's easy to verify. Actually, difficult here is not the right word. It's not like computationally difficult. It's basically that like the computation might like take a longer amount of the time, but verifying that is going to be faster. And that's basically the example of the like Anemoi like hash function. It shows that like if like basically that if you give me an input and give me an output of like the permutation. So this is actually just a small component of the entire hash function. But each of the permutation, or like actually is the S-boss here for the hash function, the input and output will satisfy 4 equation. And this is like the if and only if like condition. Basically that as long as it satisfies the following condition, it means that this is actually the valid output of that permutation for the corresponding input. And there are actually some linear relationship here, but like you can omit the linear relationship. I later will show that how do you have embed the linear relationship directly into the proof system. But basically that like in the proof system, we're actually verifying things, right? So what we are thinking is that is there a way for us to easily write these 4 equations inside your proof system? So when it actually is doing something like permutation, basically doing this like permutation of the sponge like function. So basically the like how to say that this like permutation function of the Anemoi, you are able to use very few gate, and ideally use only one gate to track these 4 equations at the same time. And the idea is, and so let me also like add a little bit detail. Basically that like Anemoi is actually, so the design actually use a fact as follows, that you can use something like x to the like 1 divided by 5. So this is actually going to be a very high degree polynomial. But you can verify that using checking a very low degree relationship. And this is basically what we are using here. Low degree is actually very important here, because if I want to embed this relationship directly into the proof system, remember that like the quotient polynomial's degree actually have something to do with the degree of your left-hand side and right-hand side of the equation. So you want to make sure that it's not too large. And in this case, we are very lucky that it can be controlled. And now the idea of like actually doing customized gates is actually solved straightforward. So this is basically our design eventually. Like there is also some optimization, and you will see that like, this seems to be very complicated. It's actually not. So first of all, we have a selector polynomial. We call that PRK3. The paper will tell you why we call that this name, because it is actually a polynomial that also serves for other purposes. But basically that this is the selector. And what is after the selector is actually just a different way to say this. So it's basically these 4 equations But like I kind of write it down in this, and you can see that why like it's more complicated is because like I also do the linear layer inside this process. So I do two things here. First of all, I kind of just translate the equation that we just saw into this equation in like Plonk. And also because like Anemoi also have linear layer, actually kind of also added a little bit constant. You can do all of those also in this equation. So basically that this 4 hash function basically do what? They do one round of the like Anemoi hash function. And the design actually doesn't really involve a lot of the like complicated technique. You do some, there are some simple optimization, but basically that like, if we look at that, you basically just like explain all the non-linear relationship. And because you know that you are actually going to do this 12 round together, usually next to each other in the proof system, I'm also using the omega. So that basically a gate will connect to the next gate. But these are basically all optimization trick here. But like the result of this is actually pretty good. Basically, is that like you can actually reduce the number of gates by like about like almost 10 times here. And it's actually not surprising because previously when we are doing degree 5, some proof system, actually the one that I'm comparing, the rescue one, does have a degree 5 gate for like the rescue. But like you also need additional gate to have reason about other things. But here, basically that I'm showing that like I can find a proof system, I can find an implementation where like an invocation of the like hash function is going to, so here 353 is basically that like, because like, so basically 14 is a round. And if you do one hash function, it become like about, actually, no. If you do the entire hash function, the number of the gates is 14. 353 is the number for like Merkle tree that is like, well, it's a little bit complicated, but it can host about 2 to the 30 like data. But that's basically the point here. Basically, the entire Merkle tree is not 3,000 gates, but 300 gates. And that like, so the O here is actually an older version of the rescue, but like it also already used customized design for that. So if you are comparing that with Gross 16 with like R1CS design, this is going to have a huger gap between that. But like people will ask one question is that how do you get this like benefit? Because that if you can reduce the number of gate, you also make all the game more complicated. But here is the point. So first of all, I'm actually like, I clearly as a cause of that, I'm using more whiles, although my proof system already have using more whiles. But basically that, yes, I'm using more whiles here. It caused the degree to go up a little bit, but also it's necessary because I already have degree 5, right? I'm already using degree 5. So if I'm not using 5 whiles, it will be actually a little bit wasteful. So basically that like, since I'm going to use degree 5, I can also do not degree 5. It will just require one additional steps. But like basically that I choose to do degree 5, and therefore I can also kind of use 4 whiles almost for free, a little bit like that. And the cost is that like you are actually doing more FFT work because your quotient polynomial now takes longer to compute. But it's the quotient polynomial that takes longer to compute, not the commitment of the quotient polynomial, because it's actually shorter. So the cost is more FFT work, but that you are actually saving MSM work just because that you are having fewer gates. And so that's like basically like the reason why it's actually faster. I actually should have like, so the number actually you can kind of just look at this because that like the majority of the cost is MSM. And actually FFT also get a benefit from that because you are actually reducing the number of gates. So FFT may be actually eventually be doing a smaller amount of the work, but that have a lot to do with the FFT space because you know that usually we do have 2048, 4092. Basically that like is not growing like really linearly. So basically that there are some complexity about whether or not FFT will actually get faster. But you can see that like reducing the number of gates give you a lot of benefit kind of everywhere in the proof system. Okay. Any question here? Okay, and I think I can go to the last point is that like, so I have been mentioning this word like for a year, although only like a few times. I never actually like start to like working on that. Basically that this actually touched something related to the like sparsity of your proof system. Basically is that like, think about this, a lot of our proof system is actually not that complicated. The Rust file that defines the entire circuit probably is less than 1 kilobyte. But the actual circuit is more complicated because, and especially when you, let's think about this, if you are using TurboPlonk, then that like talking about this like, for example, the gate that we are just doing, the hash function, you are going to require a lot of the gate. But the circuit actually can be represented more sparsely by just using customized gate. And this can actually usually give you some performance benefit. Basically that if you build a proof system that can leverage the sparsity of the problem that you are actually working on. For example, you have some structure, there are some repeated computation that are being done very frequently. You might be actually able to improve like the performance. And this actually leverage several things that are very special in the proof system like we are using. First of all, there is something different between elliptic curve and like and the proof system that are based on stack. And also Daniel is here. I really want Daniel's like input on this. Basically that like if I'm doing stack using FRI, even if the number is mostly sparse, like a lot of the zero, I am not actually able to leverage that. But if I'm doing elliptic curve, where I was committing data that are actually of a very small number, like probably like the polynomial have a lot of zero, then when I was using Lagrange basis, I'm actually able to save the cost. This means that when you are using more whiles, maybe in elliptic curve based system, you are actually not paying that much for this. And for stack, you usually don't have this benefit. Is that if that polynomial is sparse or is dense, probably the cost for you to kind of like do a lot of the operation over it is not much different. And the second thing is that like just reducing intermediate variable in the proof system usually can help you to save the MSM, because think about the entire proof system. The main change is that my width is shorter. And all these elements that I'm not including in the width are actually also never the real part of the width. The width doesn't need to remember the like intermediate value of the hash function, because this can actually be derived from other width variable. Here, I'm basically trying to reduce the redundancy of the width polynomial here. And that like the last thing is that like I think the main reason that we are doing this, although that is actually made the proof system more complicated, is that especially in Plonk, the majority of the overhead is in MSM. Even for very large like circuit, like 2 to the 26, you still see MSM to be the majority of the cost. And therefore, like switching MSM with like FFT by using more customized design is usually kind of very worthwhile. And that's basically all the slide that I have. Yeah.
What do you think about taking the trade-off space further and having higher degree custom gates? At which point does this, for I guess for Plonk, no longer make sense?
That actually kind of like, so first of all, if we are doing like very, very high degree, usually that is no longer practical. So basically that the degree here, I believe that like usually really 5 is already a pretty high number, because that also means that when you are doing FFT, you need to use usually 3 times larger space for that. But like, so a lot of people know like the HyperPlonk paper, and that paper actually have a special design trying to eliminate the overhead when you are actually using very high degree. Because think about this, if I'm, for example, if I need to do an FFT, and that like I actually use a degree 32, actually it's not degree 32, it's degree 32 times m, like relationship there. So that like actually the degree go up very high. MSM FFT may start to have complain about that, but like if you are using HyperPlonk, the issue will be much smaller. The only thing that I would say that I'm waiting for an answer is that like what are some use cases where you are going to see very, very high degree gain? I assume that like in some situation you might see that, but like in hash function, we usually don't do that. And a lot of the hash function, as you see, have already been trying to reduce like the alpha value as much as possible. So basically that like I don't see a lot of the like example of very high degree like relationship.
Well, do you not think that you could trade off a certain number of rounds theoretically for having higher degree gates?
In Plonk, it actually kind of translate to like the number of gates because you have the permutation polynomial that have by this relation, like basically these different data together. I would say that it really is about this, is that whether or not you can actually leverage that. Like when I have a high degree gate, does your circuit actually is able to leverage that? Because one thing that is actually like kind of restricting everything here is that like you also have like basically you have an equal side here. That's if you have raised something to a very high degree, you need to like make sure that you are able to use that. And if your circuit, how do you say that if your circuit have like, but actually I think you point out a very good point. What if I combine two routes into one gate? That's doable, although we know that the cost is that like, first of all, that degree will go to 25, right?
Yeah, that's true.
That I
That's
think
not
is the
ideal.
part that starts to
Yeah, that's
cause the
not great.
problem. Because if you are doing 5 and another 5, basically you separate that into 2 gates. You know that like basically I'm just doubling the number of gates, right? But if it goes to something like 25, the quotient polynomial is now almost 25 times larger. Actually 5 times larger, right? So that become a problem. And also this really depending on the rest of your proof system, is that whether or not the rest of the proof system is able to take the advantage of here. Because let's think about this, is that if I do 25, this optimization only apply to the like basically the hash function, and the rest of the proof system is actually not benefiting from that. But the number of the gates, which also affect like the cost to commit the quotient polynomial, is the number of gates comes like the degree, right? So you might be actually having a lot of the gates that are actually not using this like high degree relationship. Which actually suggests one thing, is that if in a proof system, you do have some high degree relationship, maybe it would be a good idea to use a separate quotient polynomial for that. If you are also able to reduce, basically that I have separate the gates so that like gates that are with very low degree does not affect the gates with a very high degree. But this will require you to kind of like have a special version of your permutation check, because you know permutation check have something to do with the number of whiles and so on, right?
Could you explain a bit more how you're computing the quotient? I think it might be different from the way we do it.
Yeah, let me tell. I think I will need to share that like original paper. So give me 1 second.
Mm-hmm.
But you can imagine that the differences is basically that like so remember that when we are computing a quotient polynomial, we have an alpha, right? And we have been using the alpha for, so basically let's talk about the original part. You have the first equation, basically quotient polynomial. We are actually backtracking a bunch of the equation, right? We are actually already checking about 4 of that. The first one is the original polynomial that is actually like basically the like input and output, basically that like arithmetic relation. The second one and the third one, actually they need to use the same alpha here, and they need to minus each other. This is for the permutation. So actually, technically, this was the same one. And you also have one that actually set the beginning point or like fix the starting point in the permutation chart. So you already have like, I would say that really is actually 2 equations. Actually 3 equations, but you are batching them. Now what I'm doing is basically that. Now I batch a little bit more. I basically having, you can see that like after alpha 2, I still have alpha 3. So basically that alpha 3 now track even more like relationship here. These 3 basically do the range checking. And you can see that this 4 is actually tracking those like polynomial. Because when we are tracking this equation, we are basically requiring that all of them need to be 0, right? Need to be 0 in the domain.
So for us, we just do the FFTs kind of upfront. Let's say our quotient is degree 5. So we'll do FFTs at the beginning to extend each wire polynomial to 5 endpoints. And then after that, like that's all the FFTs we do. Everything else is just pointwise evaluations. But it sounds like you're doing it a bit differently. You're doing it in more of a symbolic way, where multiplying polynomials symbolically.
So what we eventually do in our design is that actually we don't compute, basically we don't translate all the like polynomial into that. So basically let's not talk about FFT or IFT, let's talk about evaluation and the coefficient representation of this polynomial. And what we do is that we just like, basically this is that like you have all these polynomial, we basically evaluate them like on like each of the point in the coset so that you are actually getting that evaluation in the coset directly. And then you kind of like do the like, basically that you kind of already, so what eventually that we are doing is that you are already getting like the coset evaluation of t, and then you kind of convert that into coefficient. Basically that I'm computing t by like computing like all its evaluation in the coset.
Okay, got it. Thanks.
That's one way of doing that. I actually have the feeling that that might be a smarter way to do that. Like, but like eventually we choose to do that because the cost now, because that you are actually computing each gate kind of, or each point in the coset kind of like separately, and actually its value is really related to just like how I say that the evaluation of these also in the coset. So it's actually just a degree 5 computation for each one. But yes, I will firstly get the like coset evaluation of each of the polynomial. I think I should mention that is that like when I have all these like W1, W2, W3, W4, and actually also my selector polynomial, I first compute that coset evaluation. So that will involve FFT and like inverse FFT. Okay, I think that part should answer the questions. But this kind of, I think this type show a trick that like, I think some design might have already been using that, but basically that you can actually have several equations in the quotient polynomial and you let the quotient polynomial check them together and actually eventually only have one quotient polynomial.
Yeah, that makes sense. I mean, even Plonk itself really has 3 constraints, like 1 for the gate and 2 for the permutation check. So yeah, it makes sense to generalize that and allow more.
I remember that probably in some design that are already using, for example, lookup they probably already have. I don't know like whether they have combined that because lookup also have is a little bit different from the rest of the polynomial. But that I would say that that is another example of customization in like TurboPlonk, which now usually we call anything with a lookup as UltraPlonk. But like that's I think basically the idea here. And I'm abusing one thing here is that the how many equations you check actually doesn't affect the size of the quotient polynomial at all.
Related to the lookup stuff, I know that a lot of projects, I think many UltraPlonk variants, especially, have hash functions in mind. How do you think about? I mean, this seems like a fully orthogonal method, or like, I don't think you can combine the two. So how would you compare them? You think?
Well, I would say that like whether or not to use a lookup really depending on like whether you have some of the like kind of computation that would benefit a lot from like having a lookup. For example, if I'm doing like non-native arithmetic, I think there are examples showing that this will be beneficial. In some situations, range checking may also benefit from having a lookup table. And then when we are actually doing, I think another example that is good for lookup table is like related to some special hash function like reinforced concrete, which they actually want to use like a more general like SBOS, which they will use like a lookup table. My feeling is this is that if you are not using any of like the example here, like if that is not the majority of your computation, then maybe a lookup is not necessary. But if I'm, for example, if I am in a project where I do need to, for example, use reinforced concrete or like hash function that are similar on that line, then I probably really will be using lookup. Because also the reason why we use a lookup table for that is because the SBOS cannot be easily expressed as a bunch of the like low degree polynomial. And I think the reason we do that is also because I think in example like reinforced concrete, we basically want to optimize like the speed in like CPU.
Yeah, makes sense. So thinking about the kind of, I guess, optimal hash function design, which we touched on, I'm not sure if you're gonna have a real response to this, but one way of viewing, I suppose, just one instantiation or running through the Anemoi hash function once would be as a polynomial of degree something like 5 to the 13th, right? Like composing the rounds in the single gate. Do you think that this needs to hold more generally for the soundness of the security of the hash function that you need? You need it to correspond to such a high degree polynomial. I don't think Grosvenor basis attack should be, feasible within much smaller polynomials than that.
Yeah, this actually have a lot to do with like a special term in like this error, like basically this hash function. I feel that this is a term that probably will be bring up even more. As you can see, the reason why I need 14 gates is because that like they have about 12 rounds. So basically that the number of rounds is actually quite related to here. And I think one question I probably kind of mentioned that earlier in the paper is like, how to say that, like whether or not I can expect hash function that have even fewer rounds, like fewer than 12. And the problem is that like it's a little bit difficult. Actually, let me think, like let me see where it is. Okay. I mentioned the end game kind of for this reason. It's because that I kind of have the feeling that it's a little bit not easy to kind of reduce like the number of rounds in like this like polynomial easily. So the reason is because of the S-balls. That is that by having S-balls separately and having like some linear layer between each one of them seems to be very important to defense against some of the attack. Because if the input output can be expressed just by one or two simple polynomial, then actually this is pretty weak, because that like it might be actually quite easy to find solution, but like having a few more, you are like have increasing the security. So I would say that this is that, remember of the example that you mentioned before, that like why not just like multiply to basically combine two equations together so that you have a degree 25 gate, right? You are also reducing the number of the polynomial by half, right? Number of the equations by half.
That is true, but on the other side, finding a Grosvenor basis, I think the difficulty of that is also, it's at least, I think it's either polynomial or exponential in the degree. I think it might even be exponential in the degree of the system of polynomial equations.
And that's basically that why I feel that like one challenge is to kind of further kind of bring this number down, have a lot to do with like how many rounds you can control. And that, so related to round, we know have two things. First of all, like increasing alpha usually is not helping a lot. Usually is that like, yes, with a higher alpha, you might be able to reduce the round, but that's way too slow. That's that like, for example, if I change 5 to 11, probably the number of rounds is kind of still roughly like that. And a lot of the security analysis, they need to defend against other attacks. And some of these actually can put you a lower bound of the number of the rounds. And so a lot of the factors are like that affecting here, but basically that the number of rounds is not, it's not likely that you can reduce that into, for example, 4 rounds in any way, based on the current understanding of like this function.
Due to attacks which don't have anything to do with Grosvenor basis, then?
I am not an expert there, but like,
okay.
How to say that, my feeling is that like, I never, how to say that, I never like fully understand the entire like, I will not say security proof, but basically a calculation of like basically how like these different hash function defense against the attack and how we select like the number of rounds. But like you often see that there's some sort of like maximal minimal there, right? That's basically what I have been like thinking, is that like this actually is like this result combined the result from several analyses that is about like, for example, the attack, and not all of them are like related to, not all of them are like just that basis. Basically that there are other ones, for example, in the, actually one interesting one, in the middle. If you have too few rounds, that might actually cause a lot of the trouble for that. So I would say that this is actually one thing that is like kind of worthwhile to look at, is that like, is there a way to reduce the round further? By the way, another way we know that might reduce the number of rounds is that you have a wider input. So if you are hashing a lot of the elements together, you might be able to reduce the number of rounds. But like the overhead for that might also go up a little bit. Why? Because that if I want to use the same way to express the hash function, I need more input whiles, and you know that more input whiles may also bound up like the degree of the quotient polynomial. So one thing I need to admit for this paper is that this technique doesn't work very well when you really want to use a very high alpha, or like you have a lot of you want to put a lot of the input together, because in that case, I do need more whiles, or like even put the quotient even higher. But I just find that like in a lot of the application, especially for Merkle tree, where compression in the middle will actually be dominating the verification cost, then like you actually benefit from having small like hash function that takes small input and produce only one output. Okay, other questions?
Hi, Weikeng. You mentioned you could also instantiate this S box with alpha equals 3 for particular curves, right?
Yeah, just more for this like specific one that we are using. For 3-1, it doesn't work. But yes, that will be a preference. I would say, actually, let me type drawn to like because I do have some discussion there related to the situation when it's actually 3. Other I explore like optimization. Okay, here. Basically, that if you are lucky enough that q minus 1 doesn't have 3, then like alpha equal to 3 can be actually suitable for the like S box. This is beneficial because that like you probably can reduce the number of the while. And we didn't consider that. Okay, I think the only reason we didn't consider that, I think there are several things. First of all, like for the curve that we are thinking about, BLS 3A1, this doesn't fit. So basically 3 is not a suitable like alpha there. And I think another reason that like in our proof system, we already have other high degree gate. So that like in that case, degree 5 is actually doable. Also, if you use 4 whiles, you also have to get degree 5 kind of like almost for free. But like actually, we also mentioned here is that like if I use a higher alpha, like I mentioned that it's not worthwhile in general because that like you use a higher alpha, the number of rounds doesn't go down that fast. So. And we actually also discussed like some like idea that people may have is that like what if you want to use more whiles? What is the overhead with that? And that like we also mentioned that like because the round t in our system is that we kind of fix that into like a few polynomial. But like we know actually round t also have some structure. We have been thinking about whether or not you can kind of leverage that. Our idea is that like probably it's not worthwhile. So. But the paper does mention a few like optimization trick, which actually I would say that just cut the cost like even further down, reducing the number of polynomial and mostly doing that. And I think this is a good one to point out. Basically that like we basically reuse like we have some polynomial that are actually constants in the proof system. We still use a polynomial to represent that because they only show up in certain gates. And like, but basically that we can actually also use that as the selector polynomial just to make sure that this polynomial is equal to 0 when that like gate is actually not doing this hash function. Okay, and I think I can stop sharing.
So the idea there is that you, instead of having the polynomial only take binary values over the, interpolation domain, you just have it take either 0 or whatever you want it to be for the sake of that gate.
Yes, and especially you only index everything once. And also this indexing is going to be easy. Why? Because it has structure. So yeah. This actually involve one copy is actually related to, because thing about this is that a lot of the time when we actually think about that, like increasing the number of like selector polynomial, they have some benefit. First of all, they doesn't increase the like proof size, they only increase the verifying key size. And second is that if this like there's a lot of zero, you are also not committing them when you are indexing. And also indexing is a one-time effort.
Yeah, that's neat.
But also one thing is that like this actually kind of made the, I would say that proving key doesn't need to start off that because we are using universal setup. But basically that like if you want to, because if you want to do everything efficiently, you will be already computing the coset evaluation of all these like selector polynomial, which means one thing is that in Plonk, if you want to do a lot of the proof, like for the same circuit repeatedly, you are actually able to reuse a lot of the like number and computation here. Like for example, all this like coset evaluation for like the selector polynomial. And actually when you are dividing the vanishing polynomial, you can compute like the inverse of the vanishing polynomial first. But also a lot of the time that like dividing by vanishing polynomial is also a very interesting topic because actually it's very structured. It's actually not a very complicated division. So. Okay, I think if there are no other questions, then that will be all for today.
Thank you again.
Thanks everyone.
Yeah, thanks for your time.
And
Thank you.
Bye-bye.
Thanks.